70 kilograms to be specific. Moving on, next example. A heavy ruler is placed on a pivot as shown in figure 4.7. A weight is hung from the right end of the ruler and the mass of the weight is adjusted until the ruler is balanced and horizontal on the pivot. The ruler is 1 meter long and symmetric, and the fulcrum pivot point is positioned 20 centimeters from the right end of the ruler. Mass of 2 kilos will exactly balance the ruler. What is the mass of the ruler? Okay, follow along. Okay, so remember we're doing the left hand side equals the right hand side torques, or the equilibrium, this and that. This one doesn't make sense though, because we don't really have any force acting here, right? There's nothing pulling this down, making sure it doesn't go up. Well, what I introduced to you is the concept of the center of mass. The center of mass is almost always in the middle, right? So this ruler is 1 meter long. The center of mass would be around here, where it's like the halfway point of the 1 meter. Okay? And what we can do, if you think of a ruler, or if you think of any object in general, the mass will be evenly spread out across the whole thing, right? But when you're doing physics, you almost always assume the center of the mass is acting at the object's center, right? So you assume the mass is acting right here in the middle of the ruler. It just makes things easier. And even think of you holding a ruler, right? Think of you balancing the ruler on the middle of your hand, right? Even though the ruler is only touching the center of your hand, or even a pen, ruler, pen, whatever, you balance it on your finger. Even though the ruler or pen is touching touching the center of it, you can still feel its whole mass. It's sort of like that. So we assume the mass is acting on the center, and this allows us to calculate the moments. So now we've got two moments. We've got this left moment here, right? And what is it? Remember, we're trying to find the mass of the ruler. So it's mass times acceleration, that's the force, times the distance. And what's the distance to the pivot? We're defining this thing to be here, this torque, this moment to be here. The distance is from here to here. What's that? Think about it. Come on. Well, this distance is, well, this whole thing is 0.5, right? Half the ruler minus 0.2. So it's 0.3. So this times 0.3. So this is the left-hand side. What about the right-hand side? You should be able to figure this out on your own. It's 20 times the distance from the pivot, which is 0.2. Now, they didn't give us the gravity, the acceleration in this question, but we can figure it out. How? Well, we know this thing's mass is 2 kilos. So 2 times what equals 20? Well, it's 10. So gravity is 10. So what's the torque on the right-hand side? 20 times 0.2, that's 4. So this thing, this equation on the left-hand side has to also equal 4. So this equals 4. And what we say gravity was, it's 10. So 10 times m times 0.3 equals 4. So we do 4 divided by 3. M equals 4 on 3. Which is what? What's that like? Oh yeah. 1.333. It's all repeating. Okay. One more. The elbow joint is essentially a hinge. The forearm rotates about the elbow joint, and the muscles of the upper arm, in particular the biceps muscles, attached to the bones of the forearms below the joints. Okay, so they've taught us our joints, our pivot, our axle. It's right at the elbow joint. In this example, we will calculate the force which the biceps muscles must apply to the forearm to hold a 4 kilogram weight horizontally in the hands. Let's look at this diagram. It's a very loaded diagram, right? Look how big it is. Allah. You should know this question better than me, because I don't know like anatomy and all that. But let's have a look. What did we say the pivot was? It's at the elbow joint. This is our pivot right here, right? So if you think about it, the bicep muscles, they only have access really to this section, right? This sort of section. But they have to carry this whole forearm. So it's a bit of an unbalanced pivot, but whatever. Okay? So let's think of, like, if this weight wasn't here, if this 4 kilo weight wasn't here, what does your bicep have to hold to keep your forearm straight like this? Well, it has to carry what? The weight of your forearm. The weight of your forearm. So let's figure out the moment of the forearm itself. Well, remember, torque, let's say torque of forearm equals the mass of the forearm times the acceleration due to gravity times the distance from the pivot. Now the forearm, it's very long, right? But what do we do when it's very long? We don't want to calculate the whole thing. We just do the center of mass, and they've conveniently given it to us here. This COM means center of mass. So we need to find the center of mass, and they've said it's here. It's here. At the center of mass, how far are we from the pivot? Look, it's told us it's 15 centimeters. The elbow joint is right here. The distance is 15 centimeters. We have the. How about mass? What's the mass? I think they told us here 2.5 kilos. Did they give it in the question? They haven't given it to us in the question. I think just from the diagram, they gave it to you in the diagram. So the force of the torque of the forearm, sorry, let's say gravity is 10. So it's 2.5 times 10 times the distance, which is 15 centimeters. Now the next part is the other torque we have to deal with, which is the weight. So the weight is 4 kilos, right? And gravity is the same, 10. And what's the distance? It's 40 centimeters, the length of the forearm. So times 40 centimeters. I don't know why I'm putting the units, doesn't matter. Okay, there we go. So that's a torque on, actually that's it. What's the question asking? In this example, we will calculate the force which the biceps must apply to the forearm to hold a 4 kilogram weight horizontally in the hand. Okay, so the force it needs, well, how do we find force? We're looking for this force right here, right? This force right here. Well, torque, which said torque, equals force times distance. Well, what's the distance? They gave it to us, it's 4 centimeters. And we need to find the torque on the left-hand side and divide it by the distance to get the force. Okay, let's first calculate the moments on the right-hand side. Well, we just said it's these two. This one's from the forearm and this one's from the ball. So let me just use the calculator to add them up. So 2.5 times 10 times 15 plus 4 times 10 times 40. So on the right hand side we have 1975 total torque. On the left hand side our torque is the force, which we don't know, times the distance, which was what? 4. So 4F equals 1975. So what does F equal? Equals about 494. So yeah, it just goes to show how strong your arms are. 494 newtons, how much force is that? 1 newton is the force required to accelerate 1 kilogram by 1 meter per second, I think it was. If we divide this by gravity, the mass is 49.4. So about 50 kilos. So your bicep, just to carry your forearm and this weight, has to supply about enough weight to carry 50 kilos. I don't know, something like that. Interesting. Let's move on. Final example. Okay. In preparation for a backflip, a diver weighing 80 kilograms stands on the very edge of a diving board, momentarily supporting all of their weight on their toes, as shown in figure 4.9. So it makes sense. They're on a diving board, they're at the very edge, they're on their tippy toes at the end of it. The diver's feet are 20 centimeters long, and the Achilles tendon attaches at the heel and provides an upward tension force at this point. The foot articulates about the joint located 4 centimeters from the heel. Assume that the only contact force between the foot and the diving board occurs at the very end of the feet, 16 centimeters from the ankle joint. What is the tension force in the Achilles tendon, and what is the force exerted downward by the ankle joint? Okay, I'm very lucky they gave me this diagram, because I don't know what all these things are. The Achilles tendon, the heel, articulates. You guys should know this, I think. But here's what I can tell. The joint is the pivot. The joint is the pivot, maybe around here. So we've got two torques, right? We've got the torque of the Achilles tendon, pulling your body up, of course. You've got to hold your body up. And you've also got the weight at your toes. Your toes are pushing up against your weight. That's what I could make out from the diagram. So we've got these two torques. And as always, they're acting in counterclockwise directions. This one's going clockwise. I'm thinking of a clock. It's going that way. This one's counterclockwise. It's going that way. Okay, they have to be equal. What they ask us? What is the force exerted downward on the ankle? What does that mean? Anyways, let's let's calculate the torques. So on the left hand side, the torque equals the F of tendon times the distance of tendon. So it's these two. Well, what's the force of the tendon? Do we know this? I don't think so. Distance from the tendon, it's 4 centimeters. So 4 times F of tendon, and that equals the right hand side torque. What's the right hand side torque? It's the force of weight. The force of weight. What's the force of weight? There's a mistake you can make here, a very easy mistake. We're not doing 80 kilograms, we're doing 40 kilograms. Why? Because he's got 2 feet. The weight is spread against both his feet. So the weight is 40 kilograms, that's the mass, times gravity, let's just say it's 10. So that's 400 newtons. And to find the torque, it's 400 newtons times the distance from the foot, which was 16, or that's 16 centimeters. Let's keep it in meters. Let's keep it in meters. So 0.16 meters, which equals 400 times 0.16, which equals 64. So that's the right torque. I think they want us to find the force on the tendon. So this left torque equals the right torque, which is 64. So the force on the tendon equals 16. Beautiful. Okay, I'm wrong. Oops. So easy to make mistakes, huh? I converted this one to meters, but I didn't convert this one to meters. So what's 4 centimeters to meters? That's 0.04 meters. So F of t equals 64 divided by 0.04, which is 1600 newtons. Okay, what's wrong with my writing? 1600 newtons. That makes much more sense. How can the force of the tendon be just 64 newtons when you're carrying 40 kilograms of weight? Doesn't make sense. But yeah, that's it. That's the last example. There's a quick section here on static stability and static instability. What it's saying is, like, let's say you move a block, right? Will it fall over, will it topple over, or will it go back to being normal? It's saying that happens when the center of gravity moves past the base of support. So this is the base of support, right? If this moves past it, if this line goes past, it'll fall over. Just like this example right here. The center of gravity has moved past the base of support, so it's gonna fall over. Maybe a better example is like a glass, right? A glass, you tip it over a bit, will it fall down or not? It depends on the center of gravity and the base of support. And then there's summary. Actually, you don't even need to read this and that. Just read the key concepts and the two formulas we have: the torque formula, and that the sum of the clockwise and counterclockwise torques is equal. And that's it.